Good evening, everyone. Tonight we're going to be looking at the number e and the natural logarithms. So as we go through learning about the math world, there are some specific numbers that come up more often. So we're going to be looking today at the letter e. So just like pi, e is an irrational number, and it's most closely equivalent to 2.72. We're going to be using an exponential modeling. So as I look here at the graphs, I want to know which one could be y equals e to the x. So first, going through on the calculator, you could graph them all in and think about what they could be. This first function right here, we can see that that is something of the second power, and because it's not hitting the x-axis, we know that it is not going to have real roots. In number 2, I can see it increasing, and number 3, I see a function decreasing, and in number 4, it's changing. First it's increasing, then decreasing, going back up. So as I think about this e is just a number, just an irrational number, and as I raise it to powers, it's going to get bigger. So the correct choice is number 2. Reasoning for that, we would say, okay, it's going through that e is a value bigger than 0. Raised to bigger numbers is going to only create bigger values. And e ends up being very helpful when we're going through and solving problems. So let's take a look at example number 2 here. We have the population of llamas, who doesn't, on a tropical island, and they're giving us the equation right there, where t represents the number of years since they were first introduced. So the first question, A, is very straightforward. Okay, how many llamas were originally there at time t equals 0? So you will write down p equals 500 times e to the 0.035 to the 0. Now again, you can always just store that in, the 0 for t, and then plug that in. But since we've got a minute, let's just think about what happens here. Power to a power, multiply. So that's now e to the 0. Anything to the 0 power is 1. And then 500 times 1 is 500. Okay, now that was pretty straightforward. Algebraically, determine the number of years for the population to reach 600. Round your answer to the nearest tenth of a year. So we'll have to come back for that. Now, the population of llamas is a p equals. That is my variable p. So we know now that we originally started with 500. We're going up to 600. So 600 goes in for p. And then we're raising that. So the first thing we're going to do, divide by 500. I'll get 1.2 equals e to the 0.035 t. And now we're going to work with our logs. That's what I would need to get that variable out of the sky. Important here now, because it's a base of e, because we would write log base e of 1.2 equals the 0.035 t. Instead of writing log base e, that is a special case. That is the natural log of 1.2. And they help you on your calculator by keeping this a little secret, that the natural log button and the e button basically share a button. So you have that right there. Then divide by 0.035, and you will end up with t equals 5.209. So to the nearest tenth will be 5.2 years to get up to 600 llamas. So now we're going to look at the back. So knowing that the inverse, we've talked about this, where you switch the x and y, The inverse of e to the x is known as the natural log. It's going to come up often, and as we talked about earlier, that's log base e. So now without your calculator, we're going to go through these. We know that we just said natural log is log base e. So if I was looking for that variable, e, loop it around, e to the x equals e. Well, the only way to get the same base would be x equals 1. Here, I'm going to take this apart. I really want to know what this is. Remember, the base of a natural log is e, so e to the x equals 1. What is the only thing that can give us a value of 1? Well, that's 0. In C here, now I want to use those power rules, those 3 rules we've talked about. This 5 right here is the exponent. I can write that in front. And now, from the first example I learned, the natural log of e is 1. So 1 times 5 is 5. I'm going to leave you to do D. And first you're going to remember that this radical is an exponent. It's e to the 1/2. So go ahead and try to find out that answer. Now in number 4, it's the same properties we've been dealing with earlier, the multiplication, division, and power there. It's just using natural logs instead. So you're going to go ahead. First, I suggest, because it's multiple choice, that you try the store method so that you know which one is the right answer. And then you can expand that out using the logs. And now it just happens to be natural logs. Okay, lastly, we're going to be looking at a real life example here. So we have a hot liquid cooling in a room whose temperature is constant. Its temperature can be modeled using exponential functions shown below. The temperature T is in degrees Fahrenheit and is a function of time in minutes. So as we go through, we can see the 2 variables, and they're first asking us, what is the temperature, the initial temperature, and they're saying m is 0. So I'd like you to go through, do that one right now. Remember, you're going to be asked anything raised to the 0 power. And when you finish that, I'm going to tell you the answer is 168. So hopefully you came up with that as well. In part B, how do you interpret the statement T of 60 equals 83.7? So first we remember that the variable inside right here is my m. So I'm going to say after 60 minutes, the hot liquid, hopefully it's coffee, has cooled to 83.7 degrees Fahrenheit. Now C is asking you to figure out when it will reach 100. Since it started, remember, at 168 here, we found that by plugging in 0. So I'm going to start you off. We would have 100 equals the 101 e to the negative 0.03 m plus 67. So my first step, subtract the 67 over, and you end up with 33. Next, divide by the 101. You get a lovely decimal there. Make sure you're using the whole decimal in your calculator. And now it's when we use the inverse, so we're going to say, okay, base of e, that is specifically a natural log. Okay, oopsies, equals negative 0.03 m, that's small. And then dividing by the negative 0.03, I will get m equals 37.29 and 37.3. What's another way I could have done this? Once I've got my equation right here, once I've set that up that I knew what the y value was, yes, I have to do it algebraically because they asked me to. I can always put that in the solver, find out what the answer is. I can go through, I can graph it if I want to see it visually and find the intersection. You want to do whatever is going to help you get to the point of the answer, and then you can work to it. All right, how many degrees were lost per minute over the interval? Round to the nearest tenth of a degree. So they're saying on average, they're lost per minute. They're looking for the average rate of change. So for the average rate of change, I'm going to need 2 points, and you're going to plug those in. Okay. And then you will take the average rate of change, looking at the change in the y's over the change in the x, and you can finish that up. Have a wonderful night.